Okay. Hello, hello. New room, upgraded room, better lighting, better angle here on the camera. Let's go ahead and move on to the von Neumann stability test, okay? Now, this is a test that we're going to do on the finite differencing problem. So we're still on the bar, on that metal bar. I'll draw it out over here. Okay, we've got this metal bar with we call the amount of segments about 100 in the Python tutorial, so let's keep that number. I like that. And so this side's going to be raised to 350 Kelvin. This side's going to be raised to 400. And it was initially at 300 Kelvin in the middle. Okay. So we're on the same problem. Okay. So von Neumann stability, right? What is the von Neumann stability test? Well, actually, with a lot of partially derived formulas like this one, there some equations remain unstable, right? What does unstable mean? Well, as we saw in the Python tutorial, I think we know what unstable means by looking at that graph that was formed when we punched in the R value of 0.55, okay? That graph was oscillating uncontrollably and it was very hard to read. As an engineer, you can't really do much with with a crazy oscillating graph like that. Maybe you can for some applications. Maybe if you just want to see how the overall trend is or what kind of the middle ground is, the mean value of everything. But overall, we can definitely tell that that was an unstable graph by just looking at it, honestly. So oscillating, yeah, pretty unstable. Okay. What the von Neumann stability test does is, well, it tests for that stability. And how are we going to do this test? Well, good question. We are going to go ahead and remind ourselves of the beautiful, beautiful, beautiful Euler's formula. Euler's formula. Why are my notes? I'm all discombobulated. Euler's formula, right? Going back when we took differential equations and, of course, just general background knowledge. Let's write this over here. We've got Euler's formula. We're going to introduce this again. Now remember, this equation is technically, right? Technically, a Taylor series expansion, like we explained. Remember when we were using the Fourier's law, right? The Fourier's law to substitute in to make that more technical and accurate and simplified. Fourier's law is a Taylor series expansion that we substituted for all of those values that we were looking at previously, okay? And if you don't remember that, feel free to check out the first video of this series again. All right, Euler's formula. Let's just get it started. First one, we'll just get a bullet list of some examples here. E to the I to the kx, let's call it kx, okay? That's going to equal cosine kx plus I sine of kx. Let's see. So, man, when is the last time I played around with the Euler's formula in college? It must have been last semester, all the way back in the spring. Okay, so let's keep it going. What if we turn the power to a negative power? Let's see. Oops. I'm going to write this all out and then show you all. Okay, that's in the negative power form. Let's keep going. Let's keep going. What is cosine k of x? Again, this is like taking me to last semester. Oh my goodness. Thank goodness I am practicing it again in this class. It's a very useful transformation. Okay. As I get this all written out, you can kind of try and remember Euler's formula. Of course, Carlos will not need to look back and remember. Okay, divided by 2. Let's see. Yeah, that's what I want to cover right now. Okay, let me go over here real quick and walk us through some of these transformations, okay? So e to the I and kx, by the way, normally this formula is written out like the following. E to the I to the x, okay? And that equals cosine x, blah, 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 blah. Let's just call this x for now. I mean, it's just one variable. That's why I put it in parentheses. Okay, so I put it all in parentheses as I fix some of them real quick. Okay, so let's just assume that that's, you know, like it's just like x, right? It's e to the I to the x equals cosine x plus I sine x, right? So let's not forget that. Easy stuff, easy stuff. Okay, let's go. Let's get this going. So we've got the e to the I to the kx is equal to cosine kx plus I sine kx. On the other hand, e to the negative I kx is equal to cosine kx minus I sine k of x, kx. Okay? What is cosine kx? Cosine kx is simply e to the I kx plus e to the negative I kx over 2. Okay? Over 2. That's what this is saying. This is saying cosine kx is these two values combined divided by 2. Okay? Divided by 2. Awesome. What's sine to the k of x? Well, it's the same thing except subtraction sign. Okay? Subtraction sign. So, now, where do we go from here? Well, this equation can actually technically be written out as a Taylor series expansion. Well, what is a Taylor series expansion? I'm about to show you. T, write this even bigger. T equals the following. Okay, so what in the heck just happened? Well, as you can obviously tell, we've got two Euler's formulas at play here. So we could rewrite this, but let's not do that yet, or at least for a little bit. Okay, what is this value right here? What is this CK value? Can we see that good? Yes, we can. This is just going to be our constant. Okay, this is the constant in the Taylor series expansion. Okay, let's look at what is the initial value set at? Well, it's set at k equals negative infinity. Okay, well that's fine. What is the value that we want to reach? Infinity. Well, great. This is really a Taylor series expansion. We're going from negative infinity all the way to infinity. Okay, well that's cool. We've got, obviously this is all equal to our temperature. Okay, but we've got these two Euler variables here, these two Euler formula variables which we can play with. Okay, so let's do it. Let's oh, I've got an eraser right here. Let's make some room and make some edits here. We can keep the Euler's formula stuff for now, even though that is review. Let's keep going with what we've got. So let's remind ourselves that R is equal to the following. Okay, this is R. So we're going to replace this value again with R. So let me do that, please. Okay, that's a bit more cleaner. Now we can play with this. What is this going to simplify to? Let's take out the constant. Let's take out the summation. let's isolate t. T is going to equal e to the I k x and times that by e to the negative I k x. Okay, so if t is equal to this, right, what does the t up here need to equal? What's this t? What's that t? We need to incorporate the Taylor series expansion form of T into our heat diffusion equation in order to apply the von Neumann stability test. Okay, so let's do that. What is this T going to be and the other T's? Well, let's figure that out. So if T is equal to e to the I k x, right? We can just assume that this t is going to be similar to that. So let's write this all out though. Oh, I might need to, here, let's just stand real quick. Okay, so let's rewrite this bad boy. N plus 1 equal to tj. So this tjn isn't going to change yet. Okay, that's fine. We can keep that. That's not really our focus. Plus r to the e I k x t j n. Okay, let's stop there. Let's make this a bit more clear. Let's put this in brackets. Okay, let's make this clear. What I just did was replace, wait a minute, let's make this clearer. Here we go, times tj to the n, okay? And this is going to be plus, and there's going to be more terms, but let's break it down one term at a time, okay? So what we did here was, all we did here was substitute e to the I k x in front of tjn and replace x with delta x because that is our area of focus. Remember, just like the bar problem, we define each little segment as a delta x variable, okay? So using Euler's formula, you can find the simplified version of t, solve for t, and then substitute that in over here. Let's keep going. Plus, make sure I'm doing this right. Yep. Minus, okay, so that's a minus sign. If you haven't noticed, the TJN values are not being affected by the Euler substitution. And that is because those are the values that we are keeping. Those aren't affected by Euler's formula. As you can see, this really should be when j is plus 1 or j is minus 1, okay? Tj of n is not included in that. Okay, let's keep going. Tjn plus e to the negative I k delta x t. I need to erase a little bit of things over here. Tjn. Okay, we can keep this for now. Let's put the bracket in, make it nice and clear. Okay. Very good, very good. Perfect. What the heck just happened here? Right? We've got e to the I negative I k delta x. Well, why the heck is that? This is also going to be equivalent to the following. E to the I k delta x e negative I k okay, perfect. K squared and delta t. Okay, we're good. So basically, tj minus 1 is going to have that negative sign because we're subtracting a j value from the original, okay? Don't forget, When there's a negative sign, that means that we're subtracting, okay? That means that we're subtracting. So this is the expansion for this, excuse me, I'm sorry. This is the expansion for tj minus 1. This is the expansion, geez Louise, I'm messing up a lot today here. Oh my goodness, give me 1 second. This is tj minus 1. This is tj plus 1. This is just the tjn from the normal problem. That doesn't change. This is what changes because j is being affected and our position is being affected. Okay, now what the heck do we do from here? Well, we're going to need to break this down into another simplified form. What can we turn this equation into? What can we turn this whole equation into? That's going to translate down here. Well, as we can see, we've got two of these Euler variables here. Two of these Euler variables. Okay, we have a 2-digit here. Okay, so let's see. Out of all of these formulas, the Euler's formulas, which variable do you think we can translate the e to the I k delta x and the e to the negative I k delta x? What do y'all think? What can we use? Should we use cosine or sine? I'll just go ahead and tell you. It's going to be cosine because these two variables are both positive and they're being added. Okay, they're positive and they're being added. The 2 comes from this 2 variable right in the middle. And so then now we can create this. We can substitute this formula in for these values. Let's see what that would look like. Okay, let's take a deeper dive in this. This is the new formula, whoops, using the cosine variable. The cosine variable right here in this formula. Now, why is it 2 cosine kx? Well, let's take a look. If cosine kx equals this, we need to solve for e to the I kx plus e to the I negative kx. So we're going to bring this 2 over here. To substitute for these values right here. Okay, perfect. So we are going at a good pace here. This is good. Now let's isolate this. As you can probably tell, we're slowly getting rid of these t variables in the equation here. Well, why is that? Well, the tjn is distributed in each of these variables, so we don't need to keep writing those, okay? So imagine the tj of n values getting distributed into all of those, okay? And so if we just take what are in the parentheses here, isolate that, and take the not the derivative, but we're gonna put that in a and what is the word I'm trying to look for? It is late today. Put that in an interval. We're going to see where r is limited to. Okay, so let's go ahead and do that. I'm going to erase what's above this. I'm also going to erase this part. Let's see. I can probably just put the next part up here. Okay, so we're going from here to about here. Okay, this is the stability test. Okay, so what we're going to do is take the parenthesis part and set it like the following. Okay, perfect. So this is my interval right here that we begin with, okay? The von Neumann stability test begins from -1 to 1, okay? Woo, perfect. So now we gotta isolate this R value um, to see how is R limited in this scenario. I need some water. All right, let's do that. So what can we do first? Well, that's pretty easy. Let's subtract this 1 right here, this 1, over on the other sides. Okay, 1 minus 1 is 0. -1 minus 1 is -2. Let's keep going. What else can we do here? What else? What else? What else? Well, we can divide by 2. We can easily divide by 2 right here. Okay, now we can go ahead and take another 1 out and get the following. Less than 0. Okay, so we remove the R. We remove the R for a sec, but this translates to the following. R minus 2. And then that, obviously 1 divided by 2 is going to be 1/2. So this now is R, wait a minute. R needs to be less than 1/2 for a stable system. Okay, so now we have our limit. Now we have our limit. Just to reiterate, let's go through it again. Boom, we start with -1 to 1 with whatever we have, whatever we're having in the parentheses, okay? So nothing special there, nothing special. Subtract the 1, boom, -2 to 0 now. We divide by 2, boom, now -1 to 0 yet again. Now we move the R back and move the 1 over. We have -2 to 0, okay, with no R variable, but we can act, we can act like this middle part is R, set to -2, and that's greater than -1. Therefore, our R needs to be less than 1/2 for a stable system. Well, does this make sense for what we did in the Python tutorial? Let's think. When R was greater than 0.5, I believe we set it to even 0.55. The graph was oscillating and unstable. Now, when we set it to say 0.1, let's see, I'm going to write this graph. Let's write this graph out. It was oscillating like that. Now, when we had R is less than 1/2, we had a graph of both linear and the other ranges had curved relationships. So the answer here is yes, it makes sense. When we had R values less than 1/2, we were able to plug those in successfully into Python without the crazy, unstable, oscillating graph result. However, um, yes, I'm sorry, I was thinking if I worded that correctly. When we have a R value greater than 0.5, then we get that crazy, unstable, oscillating graph result. So, all in all, the von Neumann stability test here was successful, and we found that the R value must be less than 1/2 in order for the heat diffusion equation derivation to be stable. Thank you very much. I'll see you in the next video.